back in the deep dark past, once again, put yourself back in the 1700s. Okay, besides trying to figure out how to draw the graph, they were also trying, the people kind of on the geometry side of things were needing ways to find area, because they had this big problem. They couldn't take something curvy like this and figure out how much area is in there. They wanted to actually figure out, okay, how much area is between the curve and the axis. Assume I'm not going outside the lines here. So they were trying to find that area. It's curved. Geometry formulas don't do it. You can't do circles and rectangles. They didn't have a way to find area of some curved shape. So they were looking for it. So somebody got the brilliant idea that, hey, maybe we can approximate it. Maybe we can get close. So what's the easiest geometric shape there is to find area?
Square.
How about rectangle? Length times width, isn't that?
Yeah.
Square. What about square?
Okay. Squares don't adapt well here. Rectangles, they said, hey, babe, let's just divide this thing up. Probably not. Thanks. Okay, and so they said, let's divide this thing up into a whole bunch of little rectangles. And if I could approximate, if I could do the area of the rectangles, would that be kind of close to the area and to the whole curve? I mean, you got some gaps here where we're not, but at least I have an approximate area. It'd be kind of close. Okay, so the question is, how do you come up with area of a rectangle? What did you all say it takes to do area of a rectangle? Length times width. Okay, so their length. What's controlling how tall each one of those rectangles is?
Y.
The y-coordinate, or the value you would get when you put, y-coordinates are, in other words, the value you get when you put the number in the function.
Yeah.
So they said, okay, the length is going to be whatever you get when you put the number in the function, whatever number you're at. Okay, the width, well, did I set those rectangles up to be any certain width? You can do them all the same. They may not be all the same, but yeah. Okay, thanks, Luke. It'd be the difference from x1 to x2, or the difference from x2 to x3, or in other words, how much the x-coordinates are changing. Thank you, delta x, the change in the x-coordinates. So that's length times width. Okay. Then they said, I need to add up all those rectangles. What math symbol do we know that says sum up all these somethings?
Sigma.
Sigma. Yeah. Oh. And then we have to tell it where to sum up, where to start, and where to end. So they said, let's sum up from point A to point B. But then here's the problem. Okay, that theoretically, that's going to get them an approximate area. But what if I want the exact area?
Do a triangle.
Okay. What could I do to the rectangles to make them have less gaps? Smaller in what way? The width. Yeah, you would like them to get smaller. And here's where I get to use my magical. So here we have a nice little function with rectangles throughout it. And, you all said I should make the rectangles get smaller, which means I would need more rectangles in there, wouldn't I?
Yeah.
Right now it says n is 6. I'm going to make it go up. There's 27 rectangles in there. Is that better approximation?
Yeah.
If I went, there's 88.
Do a million and say so.
Infinity, that's what we need.
Okay, how thin would you want them to get?
As thin as possible.
As thin as how thin would that be?
Probably could have gone
Well,
like
okay, infinitely large you would want. There you go. Don't you want that width to get really, really, really close to 0 so that it's so narrow they're almost a line?
the limit of 0.
Yes. So this one goes as far as 200 rectangles, which is pretty good. But yeah, we want ours to get so small that they are virtually the same. They're just like lines that you were summing up. So if the width is delta x, we're going to let the width go to 0. Okay. Well, that was a beautiful theory. It's lovely. It's theoretically, it's great. Like, yeah, baby, I got it. But mathematically, they went, okay, we got this theory, but how do you make it work? Well, let me show you the magic. All right. This is the best stuff ever. Okay, I am going to draw you a function here. 1, 3. Okay. This is just your basic diagonal line. This is the line y equals x plus 1. And I want you, I'm about to prove my point here. I want you all, roughly. Okay, can you all, with your basic knowledge, calculate me the area right there?
Triangle and a rectangle.
Yeah, oh, very good. So, without needing any calculus, we can just do a triangle and a rectangle, couldn't we? Okay, what's the area of the rectangle?
2 by 4.
Okay, it's 2 by, it's actually 2 by 3, so the area is 6, yeah. And so this, if I do, okay, base is still 3, because it's the same as the rectangle. Height is 1, 2, 3, if I had that drawn perfectly to scale. So that's going to be 4.5, so what's total area? 10.5. 10.5. Seen that anywhere before?
Yeah, right above it.
Huh. Right above it, I had you integrate the function x plus 1 from, say, 1 to 4. And I got 10.5.
We're gonna go with pictures on set.
No, we're not. We're going to integrate, because integration gives you the area. When you integrate from that 1 to 4, that's the x-coordinate you're integrating between.
How does it make it go up high though? Like, how does it make sure you get the proper height on it?
It's doing the function, the height of the function, wherever high the function is going. It's using the height of the function every time. Yeah. So it's not dividing it into a triangle and a rectangle. It's doing the height clear up to the function, and it's adding up all. Imagine tiny amounts of skinny little rectangles in there that you are summing up, and they give you the area. So all that beautiful, all the volume stuff, and all that these thingies, we traced it. We could have just found the area of these, but calculus also then lets you revolve it around the x-axis and get the volume of them too. So
We'll do it again.
that's all integration is doing. But we revolve around the x-axis and we can find volumes then too. Once we want to find areas.
I want a nice creamy cone now.
Can you put your
What's an easy way to do just with paper, you know, so you don't need like
Okay. So let me ask you this one real quick. I just want to make sure you can set one up. So integration, I should write that out, yep. Integration represents
an area of a section?
okay, I'm writing this very general. The technical, it finds the area between the curve and the axis. I didn't say function, because we can also turn these sideways and find the area between some curve and the y-axis, and then it's not necessarily a function. It doesn't pass the vertical line test. So we just say it's the area between the curve and an axis. It can go to the x-axis or it can go to the y-axis. It'll work either way.
Meyer. There is a definite way to find the area there, isn't there?
So your definite way to find the area is to use the definite integral. Yeah. So you have a couple, actually I think this is on the problems listed for Wednesday, but I taught this so the seniors would see it here. If I drew you this little piece of a parabola, and I said, okay, find me the area. Find me that area. I got to give you a little bit more information. If you know that, let's see, this was at -1 and that was at 2, and I tell you the function is the function 4 minus x squared, okay, they're going to give you something like that and say find area. What are you going to do?
-1 to put the function in.
Yep. You're going to go -1 to 2, put the function in,
Done. What's the
integrate it and sub the numbers in. You got area.
We have to do Monday and Wednesday.
I don't, Wednesdays, you can go ahead and do it now, or we're gonna talk about it in class, but Wednesday is review.
You don't know who